Hello everyone, welcome back to the videos on software engineering. And we have in the last lecture, we have actually covered what is software, what are type of softwares, and what are the basic differences between softwares and programs. And today we are going to continue this discussion on the topic of software engineering. So, uh, so let's begin. Engineering in approach to develop a software is basically inspired, or you can say relatable to the analogy of building constructions. Okay. Now, what happens is if a mature person, everybody knows, and if you have seen construction of a building around your house or around your locality, you must have seen that it requires certain set of elements, maybe brick, maybe cement, maybe other type of elements you have seen. Now many of you understand this what these elements are, and you have seen the laborers or the person who actually puts them in place. Now while looking into it, it seems that it's easier and one can do that as well. And if you are asked to create a particular wall, you can actually create a particular wall, right? You can actually go and create a wall, because placing a brick on top of other and layering it with cements in the right proportion, you will create a wall. So by creating a wall, it may give you a confidence that yes, you know how to build a particular wall, or you can construct something. Now if you have this illusion that you can build a wall, so you are an architect now, right? And then if I ask you to build four walls, hopefully you can also do that, creating a four walls, because you have built one wall, so you apply the same concept and create a four walls. Now if I ask you to increase your to test, you build a multi-story building, will that knowledge of building a simple walls suffice the objective of creating a multi-storied building, right? No, it won't, because creating a wall is simpler, and creating a multi-storied building is really tough and requires multiple other concepts, multiple other type of informations, like knowledge, more knowledge than what you actually know. Likewise, building a small set of programs is easier, which you have done in most of you have done in your classes, in your labs. But when it comes to create a software which is much larger than what the soft program is, and which has multiple other concepts that are part of building a software, okay, which one is not aware of until unless he reads and practices it. So that's what is difference between a software and knowing a software and building a software. Okay. So software engineering might be a collection of systematic, like collection of past experiences, based on the techniques that you might have used, based on the methodologies that you might have used, based on certain guidelines that you have followed in creation of the software. So all these things, past experience, pave your way in creating a particular type of software. So I hope you understand with the analogy of construction that building a simple wall is similar to building a program. Building a multi-storied complex is similar to building a software. So by knowing that yes, I can build a wall, I know certain elements how they are like put in order, so I cannot assume that I can build a software. So, it is often the case that software products fail to meet user requirements. They are much expensive sometimes, they are difficult to alter, or debug, or enhance, and often delivered late, and use resources non-optimally. That means all these things are part of software development process, and we will see why actually these software product has all these drawbacks, or which we call is a software crisis. But as of now, understand that why we should learn software engineering. We should learn software engineering because we don't want these type of issues coming up in our product. When we are building a product, where we have built a product, we should not face such an issues. You should not have software crisis. Now, which factors are contributing to the software crisis? Okay, why these are the particular set of issues and that can lead to software crisis. These are the factors that can lead to software crisis. One is called larger problems. When you have a bigger set of problems and you are not able to figure it out how to solve it, okay, then that is when you actually go into crisis. Or you can say you have seen companies go making bankrupts, right? Why? Because they have such big problem of loan, they cannot pay it back. So that's where they go bankrupt. The second is poor project management. That means people generally don't have the management skills to actually manage the resources, maybe a technical resource, maybe financial resource, or maybe operational resource. So that's the product has having the crisis. The third is lack of adequate training in software engineering. This is the important thing that we will going to learn in this course. That means we don't have adequate training about software product and how they are built, how they are maintained, how they are altered, and what to do, what not to do. And the fourth is increased skill shortage. You don't have a skilled person regarding to that particular development technology or regarding the management process. And the fourth is low productivity improvements. So you cannot do with the four which are unbold, but what you can do is you can learn the best practices that we should follow in software engineering, ideally to reduce the crisis that we can face in future. Now, software programming or a programming is an art or an engineering. This is an open question. Any can answer, but as of now we will see a graph like this. Software engineering in short can be differentiated between craft and art, because art is consists of some past experiences, that I have some experience. I might not have worked on it. Okay, I don't have put much on it. By I am born artist. That when I took a brush, I can paint like MF Hussain. I can do that, right? But craft actually needs it has a past experience. It has a past experience. You have seen your father, you have seen your mother, you have seen your relatives, or you have seen your master doing this, and then you have actually learned that particular thing by seeing, by observing it. Okay, you don't need to have a mathematical foundation for the past experience, but actually you know that if you have seen a potter, okay, a man who creates clay based crafts, he moved a wheel with certain speed, and then he put a pressure of his hands on the clay or a mud. That pressure actually can transforms the mud into a vessel, a art, a craft, right? So how much pressure you have to put, how much pressure have you, how where you should hold the mud, it the experience. Okay, you should have a past experience. With no experience you can create more crafts, but this is unrecognized. Okay, this is unrecognized. Okay, then we move up the graph, we find something called engineering. Engineering is a systematic use of past experiences it is a systematic use of past experiences and has a scientific basis. That means that you have seen something happening in the past, and now you also understand, you also have some mathematical foundation, so you can prove mathematically that why this thing happens, why these things occur, and what is the logic behind, what is the rationale behind happening of such events. Okay, so engineering is an art. Programming can be an art, because I love to program, so I know how to program, right? But when I want to create certain things, then I need to have a basis, a scientific basis as well. Now, software engineering as per IEEE, is the application of a systematic, disciplined, quantifiable approach to the software operations and maintenance of software. That is the application of engineering to software. Okay, this is a standard definition of software engineering. It says that it should be quantifiable. That means that the thing should be measurable in terms of matrices, in terms of mathematical values. I should, if I have to deploy a code, I need to have certain humans or resources to work on coding. I should know how many people should be deployed to for a project, how many days they should work, how many hours they should work, so that I can calculate the cost. So this is called quantifiable approach. Okay, this is a quantifiable approach. The process of developing a software product using software engineering principles and methods is referred to as software evolution. And this is the software evolution based cycle. It starts with a change request. Okay, so there is a request from a customer about the change or a new request. Then what we do is we will do an impact analysis. That means we will try to assess, if we do this change, what is the impact that we have on our software product, right? What all modules will be impacted by a single line of code. Okay, we have to see all these things. Then if the impact is less, it is measurable, it is fine with us, then we have to go for planning phase, and we have to plan according to how many resources are required, what resources are required, how many days that resource will work, and how many days we will try to test and release that particular planning data. Based on the planning data, we have to do a system update, and finally after updating the system, we have to release that system so that the new change can take place. So this is a complete cycle of software evolution. Now coming to the software characteristics, we will stop at the software characteristics in this video. Software characteristics is a software is a logical rather than a physical system element. Therefore, software has characteristics that are considerably different from those of a hardware. Or some of the characteristics has been hidden by the graph. I will speak it out. I believe the students can see and understand that. Software is a logical entity. Okay, it's not a physical entity like your motorbikes. Okay, if you buy a motorbike today, it will work fine, it will work exactly what it happens, but after some time the thing actually deteriorates and you have to maintain it very frequent, right? So likewise, rather than having a update or maintenance part, software doesn't wear it out. Okay, the first line here says that software is developed or engineered. It is not manufactured in the sense as it goes with the hardware devices. Okay, we cannot use the word called manufactured for software engineering. We have to use the word called developed or engineered. Second line actually, which is hidden behind the graph, says software does not wear out. Okay, software does not wear out. Means that, okay, if we see this two graphs, this is called, this first graph in A, failure curve for hardware. It is said that it is said that there is an this curve is called in infant mortality. This is called a bathtub curve. That means that it looks like a bathtub. It has an infant mortality phase, and it has a wear out phase. Okay, now what is infant mortality phase? Okay, let us understand this. On the y-axis we are having failure rate. On the x-axis we have something called time. Okay, now in the initial phases of any type of development, where we are very close to the zero part, okay, the center of the axis. So it say that you have a higher failure rate. Why we have a higher failure rate? The reason is, when we are in the initial phase of development, there are lots of changes occurring and we are not knowing the concepts, so we fall in many times, we get up many times, and we are actually in the phase of learning. Okay, so there are lots of failures, like how you start walking. You start walking once a day? No, you start walking, you start cycling, you fall and many times, then you get up, then you fell many times, then you get up, and that's how the rate of failure was much more than what is today. Okay, now what is happening here is, you have a higher failure rate, and the rate goes down gradually as the system is developed with respect to time. And once the system is matured, this rate almost comes to a halt. Okay, it's stagnated, it is less constant rate, it's less number of failures coming up, and might be possible it's going to reduce with time. But at one time this failure rate again goes on increasing. Now what is this time? This is the time when the system has been in place for longer time, and it is now maintained for larger amount of time, like your bikes. After 3, 4, 5 years, 6 years, 10 years, it's like lots of maintenance. It needs lot of maintenance. So at one point of time, there is a wear out phase where you cannot maintain that particular hardware anymore. Okay, you have to replace the hardware. So this is called as wear out. This is the idle. The A is the idle bathtub curve for a hardware, the physical system. Now come to the B part, which is analogous to the hardware. It is a software curve. It says that suppose we are creating a software, it might again have high mortality in the initial phases, but as it is not impacted by the heat, dust and everything that the hardware is impacted, it should not have a wear out phase. Okay, ideally it should go down and it should have a flat curve after some point of time. But here what we see, the curve is, it goes down with time, the issue reduces with time, but you will see at some point of time it has the highest spike, and then comes down quickly, again a spike, come down quickly, and again a spike. Okay, why this spike? It says increased failure rate due to side effects. So when you insert a code, when you have not done the impact analysis that we have seen earlier, the impact, the change that you made in a code is going to impact, you're going to introduce further errors in that code. To fix the error, you need to have certain amount of time. So you have a higher failure rate, but this failure will be very small, but the rate will be higher. It comes down with time. So this curve, which is having spikes, is the actual curve. It doesn't remain straight or is constant for the rest of the time. It actually has it actually is having lots of issues. Small time with the development of the code, with respect to time, you are introducing more codes, and with the more code you are introducing more number of errors. At one time you have to change the code, but you cannot say that system has wear out. Yes, it deteriorates with time. Okay. So we will study about some more characteristics that the software has in the next lecture. Thank you.